Applications of pressure and liquids. In a public water supply system, water from a river or a decameter is pumped to a water treatment plant. After treatment, the water is pumped up to a water storage tank, situated higher than all the house in that area. A water tank is usually built atop the roof of each house, to store water and maintain constant water pressure. Due to the gravitational pull, water in the storage tank is maintained at a high pressure, and this enables water to flow to the houses of the consumers which are lower. A decameter is built across the river, to collect water for the purposes of water supply, irrigation and generation of hydroelectric power. A thicker wall is required to withstand greater pressure, since water pressure increases with depth. A firefighter requires a fire hose for directing a water jet of very high pressure to put out fire in a high-rise building. To produce a pressurized water jet, the water is accelerated by an electric pump, before flowing through the fire hose. A doctor uses a special mercury-filled manometer, called a sphygmomanometer, to measure the blood pressure of a patient. An inflatable cuff is placed around the upper arm of the patient, and air is pumped into the cuff until it squeezes the patient's arm, to stop the blood flow in the arteries. On releasing the air in the cuff slowly, the doctor takes the maximum blood pressure reading. At the instant he hears the first sound of a spurt of blood. When the cuff pressure has fallen to the minimum blood pressure, the sound disappears. The doctor takes this reading as the minimum blood pressure reading. An IV injection is used for injecting solutions of salt or medicine into the vein of a patient. Solutions flowing from the IV bottle into the patient's vein is assisted by gravitational pull. The IV bottle should be suspended at the optimum height, to ensure that the fluid gauge pressure of the IV bottle is greater than the pressure in the vein. Thank you for taking time to watch applications of atmospheric pressure. The diagram shows a person drinking with the help of a straw. When air is sucked out from a drinking straw, the air pressure inside becomes lower. The higher atmospheric pressure, acting on the surface of the drink, pushes the drink into the drinking straw, and enables it to be sucked into the mouth. A syringe consists of a tight-fitting piston which moves in a cylinder, with the nozzle at one end. When the nozzle is dipped into a liquid and the piston pulled up, the pressure below is reduced. The higher atmospheric pressure, acting on the surface of the liquid, pushes the liquid into the cylinder. When the piston is pushed down again, the liquid is ejected. A siphon consists of a rubber tube used to remove liquid from a tank. The rubber tube is filled with liquid, and one end is placed in the liquid container. When both ends of the tube are opened, liquid flowing out through Y creates a partial vacuum inside the tube. At point X, the higher atmospheric pressure acting on the surface of the liquid pushes the liquid upwards into the rubber tube. The difference in air pressure produces a continuous flow through the rubber tube as long as the point Y is at a lower level than the liquid level in the tank. A rubber sucker is a rubber cup that can be made to stick onto a smooth wall such as glass or tiled wall. The rubber cup is made airtight by wetting its rim, before pressing it against the wall to create a partial vacuum by driving the air out. The higher external atmospheric pressure outside presses down on the sucker, and makes it stick firmly to the wall. A vacuum cleaner operates by applying atmospheric pressure to remove dust particles. When it is switched on, a fan sucks out a stream of air from the space X to create a partial vacuum. The higher atmospheric pressure outside pushes the air and dust particles into the space X. The dust particles are trapped in a dust bag at X, while the fast-moving air is allowed to flow out from the back of the vacuum cleaner. The lift pump is usually used to draw out liquids, such as kerosene from a tall tin or a tank. It consists of barrel which has tifading piston, with a side tube near the top to act as a spout. There are two valves, A, fixed on the piston and B fixed at the bottom of the barrel. Both these valves open upwards. When the piston is pushed downwards, the valve B closes, and the valve A opens to allow air to move out through the piston. During the upstroke, A closes and the pressure inside the barrel is reduced due to the increase in volume of the air inside it. This causes the liquid to be pushed into the barrel by the atmospheric pressure acting on the liquid surface. On subsequent strokes, the liquid completely replaces the air in the barrel. After a few such strokes, the liquid will flow out of the spout. Thank you for taking
Researchers at MIT's Computer Science and Artificial Intelligence Laboratory have developed a smart carpet capable of tracking human actions. The device's tactile sensors are capable of evaluating people's postures without using visual images from cameras. It's enough for a person to stand or sit on the carpet and perform an action, and the neural network with deep learning determines what exactly the person did. The engineers are confident that their invention will be useful for medical purposes, smart home systems, and computer games to track the physical activity of users. The relatively inexpensive technology is based on pressure-sensitive film and conductive filaments with 9,000 sensors, each one converting human pressure into an electronic signal that can be read as data.
course of human existence, the most significant catalyst for growth has been our ability to draw energy from our world. Taming fire gave birth to the modern human, and drawing power from the wind allowed early explorers to travel the world. But today, we're going to explore the history and science behind one of humanity's greatest inventions, the steam engine. The evolution of the steam engine completely revolutionized our society. It opened new avenues for trade and caused mass migrations of rural populations into the newly industrialized cities. What I found most fascinating was the lessons its evolution taught us about science and engineering. This is one of the first practical steam engines, and it was used to pump water. The engine was incredibly inefficient. This machine was not going to start any industrial revolution, but it found a niche in coal mining, where its fuel was cheap and readily available. To investigate why this engine was so inefficient, let's first talk about how it works. The engine takes energy stored in coal and converts it to heat. That heat is used to form steam, which expands into a piston cylinder, causing the pressure to increase and forcing the piston to rise against atmospheric pressure. No mechanical work occurs on the stroke, because this chain can only transmit force in tension. The power stroke occurs when cold water is sprayed into the cylinder. This lowers the temperature, causing the pressure to drop. Atmospheric pressure now pushes the piston back down. We want to be able to quantify how much work is being done per cycle of this engine. To do that, we plot the pressure and volume inside the piston cylinder for one cycle, like this. The area inside is the work done, but this is the idealized PV diagram. In practice, there is a lot more energy being wasted. We lose a big chunk here because the steam is prevented from expanding to its full volume. A lot of energy is lost to the environment too. This is clearly visible with thermal imaging. The effect is made worse by cooling the entire cylinder with cold water. So an immediate improvement is to make a separate condenser. Here the steam can be cooled without cooling the entire cylinder. There are a lot more inefficiencies involved that reduce the total work done. Many of them are unavoidable, but we can improve the situation by upgrading the piston cylinder. The manufacturing techniques needed to bore accurate and strong piston cylinders were not available in the early days of the steam engine. That changed when John Wilkinson invented this machine. This boring machine allowed for precise machining of solid iron cylinders, which reduced steam leakage and made the piston cylinder stronger, thus allowing the max pressure to rise. We are starting to see a steam engine capable of sparking an industrial revolution. But this reciprocating motion isn't much use for most applications, especially with this flexible chain connecting them. What we need is rotational motion, which requires a different setup. To convert this linear motion to rotational motion, we need a crankshaft and connecting rod. We have turned this piston cylinder on its side, so atmospheric pressure can no longer force the piston back down, so we need to use steam on the return stroke. This requires a control valve to control when the steam enters and leaves each side of the cylinder. The valve is controlled by a cam. The steam engine is now working on both strokes of the engine, improving its efficiency and power. But piston engines like this do not produce constant torque. They'll pulsate in speed and torque during a single cycle, like this. This can cause vibrations and jerky movement. We can reduce this with the use of a flywheel, which stores rotational energy with inertia and evens the torque out. It's essentially a mechanical battery. David Robert demonstrates this beautifully with the V8 solenoid engine of his own creation. Here you can see the engine will continue to rotate without additional power, but the engine comes to a dead stop without a flywheel attached. The development of steam engines taught us a lot about thermal and mechanical efficiencies, and you may think that steam engines have become obsolete, but nearly all of our large power stations still use steam technology to convert heat energy, whether that be from coal, nuclear or solar, to mechanical energy. The technology has simply evolved into an even more efficient form with steam turbines. Thanks for watching.
Talk about a little electrical component for measuring temperature called a thermistor. I originally needed it for measuring the water temperature in a set of experiments, determining if cold water boils faster than hot. But just for fun, I also got it to turn on this PC fan when the heat was too high. What's a thermistor? A thermistor is usually a ceramic or polymer material with two wires connected to it. The key is that the thermistor's resistance changes with temperature. With some, the resistance increases as the temperature increases. Those are called positive temperature coefficient, or PTC thermistors. With others, the resistance decreases as the temperature increases. Those are called negative temperature coefficient, or NTC thermistors. I couldn't find a thermistor locally, but some quick research turned up that automobile coolant temperature sensors are just thermistors in a protective case, which was a good thing since that saved me having to make a case of my own. With this one, there's only one obvious place to connect to, this threaded part. So where do the two thermistor wires go inside? Well, one goes to the threaded part, and the other goes to the brass case. So I wrapped one wire tightly around the case, and after attaching a ring terminal to a wire, and finding suitable nuts, I attached another wire to the threaded part. I then connected up a meter and put it on the resistance scale. Remember, the resistance changes with the temperature. I put my fingers on the probe part and it started to heat up. Sure enough, the resistance on the meter started to decrease as the temperature increased. So it contains an NTC, or a negative temperature coefficient thermistor. To be useful, I needed to know what resistance matches what temperature. Unfortunately, I couldn't find a resistance to temperature table for this particular one, so I had to make my own. To do that, I prepared a tall container, this soda can with all the paint sanded off. I filled it with water and put the probe part of the sensor in the water. I also put in my kitchen thermometer. The long length of my thermometer is why I went with a tall container. For my purposes, I needed to know the resistance to temperature values for temperatures near the freezing point of water. So I put the whole thing in my freezer until the thermometer read near 0 Celsius, or 32 Fahrenheit. Then I took it out, connected my meter to measure resistance, and put it on my stove heating element. I then started recording the resistance on the meter and the corresponding temperature on the thermometer as the stove element heated up the water. I stopped once it reached boiling, which is 100 Celsius or 212 Fahrenheit. And here's the chart drawn using the data from my table. As you can see, the resistance decreases as the temperature increases. You can also see that it's a curve. The whole reason I'd gone through this process was to do some experiments to determine if cold water boiled faster than hot water, as some people think it does, and to find out why that myth might exist. That resulted in this graph of water temperature as it was heated up over time. But that's a whole other topic, which I cover in another video I'll point out later. Here's the fun I had making a PC fan turn on when the thermistor gets too hot. First, here's the circuit without the thermistor. It's very simple. The positive from my homemade power supply goes to the positive of the fan, and the negative of the fan goes back to the power supply. When I turn on the power supply, the fan starts spinning. Now here it is with a thermistor. The positive from the power supply goes to one end of the thermistor. The other end of the thermistor goes to the positive of the PC fan, and the negative of the PC fan goes back to the power supply. But this time when I turn on the power supply, the fan doesn't start spinning. That's because the thermistor is nice and cool at room temperature, and so it has a high resistance. The fan needs a certain amount of electrical current going through it in order to spin. But the higher the resistance in the thermistor, the lower the current is going through the fan. And the resistance of the thermistor is high enough to make that current too low. Now I use this hairdryer to heat up the thermistor. That causes the thermistor's resistance to decrease. As it decreases, the current increases. And when the current's high enough, the fan starts spinning. Notice that the fan is blowing on the thermistor, making it cool off more quickly. Here I'm showing the airflow direction using this tissue paper. As the thermistor cools, its resistance increases, and that causes the current going through the fan to decrease. After a minute or so, the current is too low to keep the fan spinning, so it stops. Well, thanks for watching. See my YouTube
Brian Agritech, and today we're going to talk a little bit about humidity and controlling humidity in your greenhouse or in your warehouse growing operation. So the effects of poor humidity management is a lot of time when you end up with humidity ranges outside of the ideal. So different crops prefer different humidities, and they function differently in different humidities. Additionally, if you have different humidities, sometimes it impacts the final product, not just the growth of the plant. So it's really, really important to understand humidity, what your humidity is, and be able to manage your humidity within a certain range in the growing environment. So for most growing environments, optimal humidity levels for most crops will range between like 85% humidity and 60% humidity, somewhere in that range. Most crops fall in the 75 to 85% humidity range, ideally, but a lot of crops are very comfortable exceeding that. A lot of crops are okay going under that. So when things get too humid, and too humid again is a very subjective term, but if things are too humid and you're starting to see disease or fungal pathogens show up on your plants and you're struggling with some of these issues, you've probably got a bit of a humidity problem and you need to know how to dehumidify. There are a lot of ways to do this. If you live in a dry environment, then oftentimes air exchanges will take care of the problem for you. Or you can rely on air conditioning, which dehumidifies through kind of the bicondensation. Or you can use an industrial dehumidifier or even a home and hobby dehumidifier for a smaller operation. So a lot of folks ask about cooling walls. Well, cooling walls, swamp coolers, that kind of thing, they work in really dry environments because they're dumping water vapor into the air, right? So that's why they work, which means that they're actually adding humidity to the air. That's typically why they're not super effective at very high humidity levels and why they work so well in dry environments. Those types of cooling things, typically, if you're growing in a greenhouse that uses a cool wall effectively, you probably don't have a humidity problem because you're already in a place with really low humidity. So humidifiers and sizing them can be a really tricky subject, especially when it comes to plants. In traditional engineering, they know how many people will be in a building exhaling. They know what the humidity level of your breath is. They know what the humidity levels outside are from season to season. They know all of the different things that are contributing to humidity in that environment. But indoor growing is such an early industry that it's really pretty up in the air as to how much water plants are oftentimes dumping into the atmosphere. So this can be a pretty tricky subject, but if you're already growing indoors, you know how much water your plants are consuming, right? Because you're having to top off your sump tank. The difference that you're topping off your sump tank, a significant amount of that is just transpirational losses from your plant. So they're just dumping that water into the growing environment. That's usually a good place to start. We also have some humidity calculators and some water vapor calculators on Able for doing CO2-based vapor, basically pounds of water type calculations. That can really, really help with narrowing down what size of humidifier you need. By and large, with our zip farms, with what we do, we tend to recognize, or we tend to use one fairly large industrial indoor humidifier for about every 500 square feet. And that's usually more than enough to take care of our humidity problems. So you'll almost never need to humidify an environment because the plants act as their own little humidifiers, right? What you need to worry about is dehumidification. When it comes to sizing a dehumidifier, it can be a pretty tough proposition. I would recommend starting by getting a hold of us or one of our folks, explaining to them what you're trying to do, how many plants you'll have there, and we do have some calculators that we've built internally that allow us to do some rough estimates of how much water vapor your crops are going to be producing. So you don't usually have to humidify because every plant is just constantly losing water. And in fact, we've got sensors placed in our growing environments, and the moment we turn on the lights, the humidity spikes. Why? Because in order to participate in some of these photosynthetic activities, all of the cells in the plant basically start to consume water. So they're pulling water up, and we've also got these the stomates in the plants opening so that there can be gas exchange. And in that process, a lot of that water the plants are pulling up just turns to water vapor and escapes into the atmosphere. Remember, the humidity levels inside the leaf tissues are saturated. It's as humid as it can possibly be in there. And so as soon as those stomates open, boom, all of that humidity zooms out of the plant and into the growing environment. And that's what we've got to take out of the atmosphere in order to avoid it getting too humid. Yeah, so when we're talking about environmental controls, it's important to remember that humidity is relative to temperature. So as the temperature goes up, the maximum relative humidity also goes up with it. So the warmer it is, the more water vapor the air will hold. This is really important because people that struggle with high humidity can oftentimes deal with it by reducing their growing temperatures if it's still within the optimal range for their crops. So it's one of many variables that kind of interact in this very complicated matrix, and extracting one variable from all of the rest of them can oftentimes be practically impossible. So what it's important to do is understand the effects that temperature, that darkness, that light, that all of these different variables that we're dealing with in our growing environment, understanding how all of those things affect, ultimately, humidity. All right, thanks so much for watching. I really hope this information was useful to you guys.
So through the winter months, typically you're not going to have as many issues with heat buildup, but you do have moisture buildup. And obviously the easiest way to deal with that is to get ventilation, to get cross flow of air moving through the house. Simplest way is you've got the doors. You open these doors up, you're going to get a lot of airflow. But if you're not here all the time, it's nice to have an automated feature. These gabled shutters above me, these work really well. They're going to be set on a thermostat and they're going to open as the temperature rises in here. It's going to help to move the air flow above and help reduce the overall moisture level, the humidity level in the tunnel. You also have the roll-up sides, and those can open as well to help with the lower ground cross ventilation. And then of course there's horizontal airflow fans that can be installed in some tunnels, and they can help to move the air back and forth as well. And throughout the winter, did you find, the greenhouse, did it have to ventilate quite a bit? What was did it heat up excessively at any point? How did it handle?
Yeah, it's a good question. It did not heat up excessively at any point. It did ventilate somewhat. Even in the middle of the winter, the automatic roll-up sides were sometimes rolling up.
Really? That's
just
great.
a little bit, and then they'd come right back down.
Great. And you have these gabled shutters as well, so they were opening. One of the benefits of the ventilation, too, is to manage the humidity and the moisture level that can build up when you get a bright, sunny day like this.
Indoor residential humidity, reducing humidity at the source, improving indoor ventilation, dehumidifying, and improving thermal window energy efficiency to prevent condensation. Condensation forms on cold surfaces as surface temperatures fall below dew point. Humidity increases with the amount of people and activities in the home. Showers, laundry, cleaning dishes, and unfinished crawlspace areas can cause indoor humidity to be unnecessarily high. In conventional Canadian homes, it becomes necessary to reduce indoor humidity with the onset of winter. As a rule, 30 to 35% indoor humidity is recommended for -5 to -10 degrees Celsius. When tackling indoor humidity, always improve the areas where the moisture is being generated. Installing good quality bathroom fans and cleaning the unit seasonally will help keep the exhaust fans effective. Cooking range and other exhaust fans should be directly vented to the exterior and not into the roof perimeter soffit. If you have a forced air furnace, check to see if you have a fresh air intake. Fresh air intakes make all the difference in reducing indoor humidity in the winter. That is, providing that they are working properly. These units often require seasonal cleaning and should be located where good quality air can be drawn into the home. Fresh air intakes should be located well away from vehicle exhaust, pellet stove exhaust, and clothes dryer exhaust vents. You can monitor your indoor humidity levels with an inexpensive humidity gauge or use a wall-mounted dehumidistat switch connected to an exhaust fan. Dehumidistats are most effective when connected to a forced air furnace fan, which has an outdoor fresh air intake as part of the return air system. There are two main types of dehumidifiers for residential applications. Each type must be correctly sized for the task. Dehumidification may not be necessary if the indoor humidity source can be controlled. Whole house dehumidifiers are more common in coastal climates due to outdoor humidity levels. High humidity in some rooms can be problematic. Kitchen, bathroom, and bedroom windows can collect moisture or frost as the glass cools below dew point. Consider upgrading to thermally efficient windows in these rooms or cover the glass with plastic to prevent condensation from forming. This prevents the moist indoor air from contacting the cold glass. Ensure that the plastic is well sealed for the plastic barrier to work properly. Protecting basement windows and skylights from the elements reduces condensation and ice from forming inside the building. These are my insulated skylight covers that I constructed and I put in place each fall, which are highly effective in saving energy, reducing moisture, and preventing roof ice. So there you have it. We've touched on reducing indoor humidity at the source, improving indoor ventilation, dehumidifying, and improving window thermal efficiency to prevent condensation.
Here from howtomechatronics.com. In this Arduino tutorial, we will learn how to use the DHT11 and DHT22 sensors for measuring temperature and humidity with the Arduino board. These sensors are very popular for electronic hobbies because they are very cheap but still providing great performance. Here are the main specifications and differences between these two sensors. The DHT22 is the more expensive version, which obviously has better specifications. Its temperature measuring range is from -40 to +125 degrees Celsius with 0.5 degrees accuracy, while the DHT11 temperature range is from 0 to 50 degrees Celsius with 2 degrees accuracy. Also, the DHT22 sensor has better humidity measuring range from 0 to 100% with 2 to 5% accuracy, while the DHT11 humidity range is from 20 to 80% with 5% accuracy. There are two specifications where the DHT11 is better than the DHT22. That's the sampling rate, which for the DHT11 is 1 Hz or 1 reading every second, while the DHT22 sampling rate is 0.5 Hz or 1 reading every 2 seconds. And also, the DHT11 has smaller body size. The operating voltage of both sensors is from 3 to 5 volts, while the maximum current used when measuring is 2.5 milliamps. Okay, now let's see how these sensors actually work. They consist of a humidity sensing component, a NTC temperature sensor or thermistor, and an IC on the back side of the sensor. For measuring humidity, they use the humidity sensing component, which has two electrodes with moisture holding substrate between them. So, as the humidity changes, the conductivity of the substrate changes, or the resistance between the two electrodes changes. This change in resistance is measured and processed by the IC, which also makes it ready to be read by a microcontroller. On the other hand, for measuring temperature, these sensors use a NTC temperature sensor or a thermistor. A thermistor is actually a variable resistor that changes its resistance with the change of the temperature. These sensors are made by sintering of semiconductive materials such as ceramics or polymers in order to provide larger changes in the resistance with just small changes in the temperature. The term NTC means negative temperature coefficient, which means that the resistance decreases with the increase of the temperature. Okay, now let's connect the DHT22 sensor to the Arduino board. The sensor has 4 pins, VCC, ground, data pin, and a not connected pin which has no use. A pull-up resistor from 5K to 10K ohms is required to keep the data line high in order to enable the communication between the sensor and the Arduino board. There are some versions of these sensors that come with breakout boards with built-in pull-up resistors, and they have just 3 pins. The DHT sensors have their own single wire protocol used for transferring data. This protocol requires precise timing, and timing diagrams for getting the data from the sensors can be found from the datasheets of the sensors. However, we don't have to worry much about these timing diagrams because we will use the DHT library, which takes care of everything. Here's the Arduino source code. After we have included the library, which can be found from the Arduino official website, we need to define the pin number to which our sensor is connected and create the DHT object. In the setup section, we need to initiate the serial communication because we will use the serial monitor to print the results. Using the read22 function, we will read the data from the sensor and put the values of the temperature and the humidity into the T and H variables. If you use the DHT11 sensor, you will need to use the read11 function. At the end, we will print the temperature and the humidity values on the serial monitor. Here's the result that we will get after we will upload this code and run the serial monitor. I also made an example where I displayed the results on a LCD. You can find the source code of that example on my official website.
Let us also create an axis that represents the angle theta. The green line rotates by the angle theta. For each value of theta, the x-coordinate represents the cosine of theta, and the y-coordinate represents the sine of theta. The angle theta can range anywhere between negative infinity and positive infinity. This two-dimensional pattern is what we refer to as a sine wave. We can change the sine wave's amplitude, phase, and frequency. Suppose we have two sine waves that are identical except for the fact that they have different amplitudes. If we add these two sine waves together, the result can be represented graphically as shown. Now, suppose that the two sine waves also have different phases. The sum of these two waveforms can be represented graphically like this. So long as the two sine waves have the same frequency, their sum will always be another sine wave of the exact same frequency, but with a different amplitude and phase. Now, suppose that the two sine waves also have a different frequency. If we add together sine waves of different frequencies, then the resultant waveform is no longer a sine wave. We can add together three sine waves. We can add together four sine waves. We can add together five sine waves. In fact, we can add together an infinite number of sine waves. Here, by adding together an infinite number of sine waves, we have produced a pattern that looks like this. Now, let's add together a different set of sine waves. By adding an infinite number of sine waves, we have produced this other pattern that looks like this. As it turns out, every possible waveform and function in existence can be generated by just adding together different sets of sine waves. In the two examples shown here, the sum of all the sine waves happened to be repeating waveforms.
Mass is equal to the product of its mass and its acceleration, F equals ma. We can figure out the sum of the forces acting on the mass by drawing a free body diagram. There is only one force, the force exerted by the spring, which is equal to the displacement x multiplied by the spring stiffness, k. And so, we obtain the equation of motion for the system. This is an ordinary differential equation, and the solution is a sinusoidal function. T is time, phi is the phase angle, and A is the amplitude of vibration. We can determine A and phi by considering the initial position and velocity of the mass. Let's look at an example where the system has a mass of 5 kilograms and a spring stiffness of 20 newtons per meter, and a vibration is triggered by applying an upwards velocity of 2 centimeters per second to the mass. Since the displacement x is initially 0, the phase angle phi must also be equal to 0. And then we can differentiate the equation for x to calculate the amplitude of vibration A. An important property that can be calculated from a mass spring model is the system's natural frequency, the frequency at which it will oscillate naturally when in free vibration. It's given by this term in the equation of motion, and is denoted using the Greek letter omega. It depends only on the mass and the spring stiffness, so no matter what the initial conditions are, a system will always oscillate at the same frequency. It has units of radians per second, so is called the angular natural frequency. But it's sometimes more practical to think of the natural frequency as a number of cycles per second, in which case it's denoted using the letter F and has units of hertz. The inverse of the natural frequency is the period t, which is the duration of each cycle in seconds. Let's compare how two different systems oscillate. Both of these models have the same spring stiffness, but different masses, and so different natural frequencies. The heavier mass oscillates at a much lower frequency. A neat demonstration of the natural frequency is the tuning fork. When the fork is struck, it vibrates at its natural frequency, which is much faster than shown here. This causes the air molecules to vibrate at the same frequency, which produces a corresponding tone. By assuming that the prongs behave like cantilever beams in bending, beam theory can be used to derive a formula for the natural frequency of the fork. The density, length, and cross-section of the prongs can be calibrated to obtain the desired tone. Of course, when a mass oscillates freely, it doesn't do so indefinitely. Energy within the system is dissipated as heat over time, so the oscillations progressively decrease in magnitude and eventually stop altogether. This loss of energy is called damping, and it occurs in all real mechanical systems. There are several different mechanisms that can contribute to the overall damping of a system. With structural damping, energy in a vibrating structure is dissipated due to the relative motion of components at structural joints. And material damping is damping provided by the material itself, where energy dissipates in a vibrating material due to interactions occurring at the molecular level. To improve our spring mass model, we can lump the damping from all of the different sources together and represent them by a single damping device called a dashpot, which is essentially a plunger that moves through a liquid-filled cylinder. Whenever the plunger moves, a force will act to oppose its displacement, and the magnitude of this damping force is proportional to the velocity of the displacement. The faster the plunger moves, the larger the damping force. C is the viscous damping coefficient. It defines the total amount of damping in the system. This model of damping is called viscous damping, because it behaves in a similar way to viscous forces in a fluid, which are proportional to the fluid velocity. There are other damping models, but viscous damping is commonly used because of its simplicity. If we include the dashpot in our spring mass model, the equation of motion is the same as for the undamped system, but also includes the damping force. It's a little more difficult to solve this equation, and the solution will depend on the amount of damping. If a system is underdamped, it will oscillate, and the magnitude of each successive oscillation will decrease until it stops. If the damping of the system is increased significantly, which you can think of as the dashpot being filled with a far more viscous fluid, any oscillation will be completely suppressed by the damping. This is called an overdamped system. And a critically damped system occurs right at the limit between these two cases. It is just enough damping to suppress vibration. With turbines and motors, occurs when a rotating component is unbalanced, meaning that its mass is unevenly distributed. This introduces a load that has a sinusoidal component in the vertical direction and can cause vibration. Unbalance can occur because components were poorly fabricated or have been distorted. But eccentric masses are sometimes added to motors on purpose. Intentionally unbalanced motors are how phones and video game controllers are able to vibrate. We can analyze this type of forced vibration using the spring and dashpot model by adding a sinusoidal external load. The resulting equation of motion is similar to the free vibration case, but is a non-homogeneous differential equation. Its solution is the sum of two functions, a complementary solution and a particular solution. The complementary solution is the solution to the homogeneous form of the equation, where the right-hand side is equal to 0. This is just the solution to the equation of motion for an underdamped system in free vibration that we saw earlier. And the particular solution captures the effect of the external loads and is given by this expression. R is the ratio of the frequency of the external force to the natural frequency of the model. Since there's damping in the system, the complementary solution that represents free vibration will eventually reduce to 0. At this point, the motion of the system is defined by the particular solution only. For this reason, the particular solution describes what's called the steady state response. It has the same frequency as the forcing function, but is offset by a certain phase angle, meaning that the response of the system lags the external force. Something interesting happens to the steady-state response when the frequency of the forcing load is very close to the natural frequency of the system. R approaches 1, and so the first term in the square root is close to 0. And if the system has very little damping, the second term will also be close to 0, which means that the displacement will become very large. Let's plot the normalized maximum displacement against the frequency ratio. For an undamped system, the damping ratio is equal to 0. So when the forcing and natural frequencies match, the displacement becomes infinite. All systems have some level of damping, so this is just a theoretical case. Here's what the response looks like for different damping ratios. We can see this effect if we adjust the speed of the unbalanced motor. As the frequency of the force caused by the eccentric mass approaches the natural frequency of the system, the displacements become very large. This happens because when the natural frequency and forcing frequency are the same, the energy added to the system by the external force is timed just right so that it increases the amplitude of the displacement with each cycle. This is called resonance. Resonance can be very dangerous and needs to be assessed carefully. It's one of the reasons it's so important to be able to calculate the natural frequency of a system. If the natural frequency of a bridge matches the frequency of wind loading acting on it, or of pedestrians crossing it, the results can be catastrophic, particularly if the structure has little damping. Devices called tuned mass dampers are sometimes installed in buildings and bridges to control the dynamic response at resonant frequencies. With a rotating eccentric mass, the external force acting on the system is a simple sine wave function. This makes it easy to solve the equation of motion, since we can obtain a neat closed-form solution. But if the loading is defined by a complicated function, or is completely arbitrary, which might be the case if it's based on test data, it might not be possible to solve the equation of motion directly, and numerical integration methods will have to be used instead. Designing
This sound right here is a pure A, 440 beats per second, meaning if you were to measure the air pressure right next to your headphones or your speaker as a function of time, it would oscillate up and down around its usual equilibrium in this wave, making 440 oscillations each second. A lower pitch note, like a D, has the same structure, just fewer beats per second. And when both of them are played at once, what do you think the resulting pressure versus time graph looks like? Well, at any point in time, this pressure difference is going to be the sum of what it would be for each of those notes individually, which, let's face it, is kind of a complicated thing to think about. At some points, the peaks match up with each other, resulting in a really high pressure. At other points, they tend to cancel out. And all in all, what you get is a wave-ish pressure versus time graph that is not a pure sine wave. It's something more complicated. And as you add in other notes, the wave gets more and more complicated. But right now, all it is a combination of 4 pure frequencies. so it seems needlessly complicated given the low amount of information put into it. A microphone recording any sound just picks up on the air pressure at many different points in time. It only sees the final sum. So our central question is going to be how you can take a signal like this and decompose it into the pure frequencies that make it up. Pretty interesting, right? Adding up those signals really mixes them all together. So pulling them back apart feels akin to unmixing multiple paint colors that have all been stirred up together. The general strategy is going to be to build for ourselves a mathematical machine that treats signals with a given frequency differently from how it treats other signals. To start, consider simply taking a pure signal, say with a lowly 3 beats per second, so that we can plot it easily. And let's limit ourselves to looking at a finite portion of this graph, in this case the portion between 0 seconds and 4.5 seconds. The key idea is going to be to take this graph and sort of wrap it up around a circle. Concretely, here's what I mean by that. Imagine a little rotating vector where at each point in time, its length is equal to the height of our graph for that time. So high points of the graph correspond to a greater distance from the origin, and low points end up closer to the origin. And right now, I'm drawing it in such a way that moving forward 2 seconds in time corresponds to a single rotation around the circle. Our little vector drawing this wound-up graph is rotating at half a cycle per second. So this is important. There are 2 different frequencies at play here. There's the frequency of our signal, which goes up and down 3 times per second, and then, separately, there's the frequency with which we're wrapping the graph around the circle, which at the moment is half of a rotation per second. But we can adjust that second frequency however we want. Maybe we want to wrap it around faster, or maybe we go and wrap it around slower. And that choice of winding frequency determines what the wound-up graph looks like. Some of the diagrams that come out of this can be pretty complicated, although they are very pretty. But it's important to keep in mind that all that's happening here is that we're wrapping the signal around a circle. The vertical lines that I'm drawing up top, by the way, are just a way to keep track of the distance on the original graph that corresponds to a full rotation around the circle. So lines spaced out by 1.5 seconds would mean it takes 1.5 seconds to make one full revolution. And at this point, we might have some sort of vague sense that something special will happen when the winding frequency matches the frequency of our signal, 3 beats per second. All of the high points on the graph happen on the right side of the circle, and all of the low points happen on the left. But how precisely can we take advantage of that in our attempt to build a frequency unmixing machine? Well, imagine this graph as having some kind of mass to it, like a metal wire. This little dot is going to represent the center of mass of that wire. As we change the frequency and the graph winds up differently, that center of mass kind of wobbles around a bit. And for most of the winding frequencies, the peaks and the valleys are all spaced out around the circle in such a way that the center of mass stays pretty close to the origin. But when the winding frequency is the same as the frequency of our signal, in this case 3 cycles per second, all of the peaks are on the right and all of the valleys are on the left, so the center of mass is unusually far to the right. Here, to capture this, let's draw some kind of plot that keeps track of where that center of mass is for each winding frequency. Of course, the center of mass as a 2-unit is relatively high, and then as you increase that winding frequency, and the graph balances out around the circle, the x-coordinate of that center of mass goes closer to 0, and it just kind of wobbles around a bit. But then, at 3 beats per second, there's a spike, as everything lines up to the right. This right here is the central construct, so let's sum up what we have so far. We have that original intensity versus time graph, and then we have the wound up version of that in some 2-dimensional plane, and then, as a third thing, we have a plot for how the winding frequency influences the center of mass of that graph. And by the way, let's look back at those really low frequencies near 0. This big spike around 0 in our new frequency plot just corresponds to the fact that the whole cosine wave is shifted up. If I had chosen a signal that oscillates around 0, dipping into negative values, then, as we play around with various winding frequencies, this plot of the winding frequency versus center of mass would only have a spike at the value of 3. But negative values are a little bit weird and messy to think about, especially for a first example, so let's just continue thinking in terms of the shifted up graph. I just want you to understand that that spike around 0 only corresponds to the shift. Our main focus, as far as frequency decomposition is concerned, is that bump at 3. This whole plot is what I'll call the almost Fourier transform of the original signal. There's a couple small distinctions between this and the actual Fourier transform, which I'll get to in a couple minutes, but already you might be able to see how this machine lets us pick out the frequency of a signal. Just to play around with it a little bit more, take a different pure signal, let's say with a lower frequency of 2 beats per second, and do the same thing. Wind it around a circle. Imagine different potential winding frequencies, and as you do that, keep track of where the center of mass of that graph is, and then plot the x-coordinate of that center of mass as you adjust the winding frequency. Just like before, we get a spike when the winding frequency is the same as the signal frequency, which in this case is when it equals 2 cycles per second. But the real key point, the thing that makes this machine so delightful, is how it enables us to take a signal consisting of multiple frequencies and pick out what they are. Imagine taking the two signals we just looked at, the wave with 3 beats per second and the wave with 2 beats per second, and add them up. Like I said earlier, what you get is no longer a nice pure cosine wave, it's something a little more complicated. But imagine throwing this into our winding frequency machine. It is certainly the case that as you wrap this thing around, it looks a lot more complicated. You have this chaos and chaos and chaos and chaos, and then whoop, things seem to line up really nicely at 2 cycles per second. Then as you continue on, it's more chaos and more chaos, more chaos, 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 whoop, things nicely align again at 3 cycles per second. And like I said before, the wound-up graph can look kind of busy and complicated, but all it is the relatively simple idea of wrapping the graph around a circle. It's just a more complicated graph and a pretty quick winding frequency. Now what's going on here with the two different spikes is that if you were to take two signals and then apply this almost Fourier transform to each of them individually, and then add up the results, what you get is the same as if you first added up the signals and then applied this almost Fourier transform. And the attentive viewers among you might want to pause and ponder and convince yourself that what I just said is actually true. It's a pretty good test to verify for yourself that it's clear what exactly is being measured inside this winding machine. Now this property makes things really useful to us because the transform of a pure frequency is close to 0 everywhere except for a spike around that frequency. So when you add together two pure frequencies, the transform graph just has these little peaks above the frequencies that went into it. So this little mathematical machine does exactly what we wanted. It pulls out the original frequencies from their jumbled up sums, unmixing the mixed bucket of paint. And before continuing into the full math that describes this operation, let's just get a quick glimpse of one context where this thing is useful, sound editing. Let's say that you have some recording and it's got an annoying high pitch that you would like to filter out. Well, at first, your signal is coming in as a function of various intensities over time, different voltages given to your speaker from 1 millisecond to the next. But we want to think of this in terms of frequencies.
can use vibration analysis alongside other technologies to get the earliest warning that that is beginning to occur, that the early stages of failure are occurring, which may end up like that if we don't do anything about it. And vibration analysis is a terrific tool for doing exactly that, because vibration analysis, in a sense, enables us to look inside the machine and see exactly what's going on, whether it's gearbox with bearings, blowers and fans and so on. We want to be able to look at those bearings, look at the gears, look at the impellers and so on, and find out what's going on. If we could look at that bearing and tell that it's lubricated properly, installed properly, there's no damage to the raceways, there's no damage to the rolling elements, then we have the confidence that we can go on producing our product and it's all good. But if we see something, then we can act. Same goes with gears, whether they're timing gears or inside a gearbox. Are they aligned? Are they lubricated? Is there damage to the teeth? Anywhere, whatever the case may be. Vibration analysis lets us look inside the machine. Now in this case we've got, the motor driving a pump and a vibration sensor sitting up on top. Now I'll explain a bit more about that in just a moment, but you may first imagine that, all the vibration is transmitted along and goes up to this point, and maybe from this side as well. And that's one of the things I'll mention a bit more about in a moment. Just where is the vibration coming from and how's it getting to that sensor? But one of the keys is that vibration analysis, in a sense, enables us to sort of listen. Well, what is happening with the shaft? What's happening with the bearings? What's happening with the rotor bars? Now we pick up all those sounds from here. They all combine together into one measurement, but separating them in frequency and some of the other things we'll explain let us do that so we get an idea of the health of each of those components. Over this side, that bearing is not in good condition. For the pump, we've got pump cavitation. On the machine head, okay, not many machines sound like that, but anyway. Okay, so the way we do this is, as you've just seen, we can put the vibration sensor up there on the bearing, and all the vibration is transmitted, through the machine itself up to that point. The sensor has to be mounted properly. That is very important, so that all those high and low frequencies get up into that sensor. But the fact is, when we mount it up on top, that is sensitive to the vertical motion. Whereas if I move it to the horizontal location, that's now much more sensitive to the horizontal motion. So, for example, if it was rocking back and forward due to looseness or resonance, then the horizontal measurement will tell us about that.
What is eddy current? The word eddy literally means a circular current. Let us now try to understand how they are produced. Take a solenoid that has a soft iron core. Now connect this solenoid to an AC source. When a metallic disc is held over the cross-sectional face of the soft iron core, the metallic disc will be thrown into the air. When current flows through the solenoid, magnetic flux linked with the solenoid increases from 0 to finite value. This change in magnetic flux gives rise to induced currents in the disc. The upper face of the soft iron core attains the same polarity as the lower face of the disc. Hence, the disc is repelled by the soft iron core and is thrown up in the air. This experiment shows that when a conductor is kept in a changing magnetic field, currents are induced in the body of the conductor. These are currents that occur in very small loops and are called eddy currents. Foucault discovered eddy currents in 1895. In some cases, the eddy currents may produce undesirable effects. For example, they increase the internal energy and therefore can increase temperature of the material. For this reason, devices like transformers, which are constantly subjected to changing magnetic field, are often laminated or their metallic core is divided into thin sheets. Each of these sheets are insulated from one another. The magnitude of eddy currents is given by I is equal to -1 by R into d phi b by dt. The direction of eddy currents is given by the Lenz's law or Fleming's right-hand rule. Lenz's law states that the direction of induced current is such as to oppose the very cause producing it.
I have an induction cooker at home on which I'm boiling water, and I thought the way it worked was like an iron box. The base would just get hot, and that heat would get transferred to the vessel and start cooking whatever's inside. But then I read that that's not how it works. The base of the induction cooker does not get hot at all. And then I tested it out. I took the induction cooker, I switched it on, and then I put my hand on top of it for a few minutes, and nothing. It wasn't hot at all. It was right. It doesn't produce any heat. But then, on that same thing, I keep this vessel of water, and within minutes, it starts boiling. So the question is, how does an induction cooker cook things and heat things up without itself getting hot? Well, that's what we're going to find out. And it turns out it's due to the science of eddy currents. So what are these eddy currents? To answer that question, let's look inside the induction cooker. If you could open up, then you might see a lot of things, but the most important one is a coil at the center. And we know that when you pass current through the coil, it produces a magnetic field. And that's exactly what happens. When you turn on the switch, there's a current that starts passing through the coil, and that current starts generating magnetic fields. But what's important is that the current is fluctuating. It's changing its direction continuously. It's called alternating current, which we'll talk about in separate videos. And it changes its strength. As a result of that, the magnetic field that it generates also keeps fluctuating in direction and in strength. So imagine this is how the magnetic field is generated. It's continuously fluctuating. And that's all that our induction cooker does. It does not produce any heat. All it does, it produces a fluctuating magnetic field. But how does that boil our water? We'll get to that eventually. But for now, instead of thinking about keeping a vessel on top of this, let's keep a rectangular loop of wire. What would happen? Well, because the magnetic field is fluctuating, we have changing magnetic flux through a coil. And from Faraday's law, we know that that produces an EMF. And as a result, there will be an induced current in this coil. Now, the direction of the current will all depend upon whether the magnetic field is increasing, decreasing, what the direction is in terms of Lenz's law, something all we have talked about before. But don't worry too much about the direction as of now. What's important is there is an induced current due to the changing magnetic flux. But now comes the question, what if instead of having a coil like this, what if we kept a rectangular plate? Now what would happen? Well, again, the flux is changing, so there is an induced EMF. But earlier, there was only one path for the current to flow, but now the entire thing is a conductor. The whole thing is a playground for the electrons, which means your currents will be formed in loops everywhere on the surface of this conductor. And so you'll have loops of current formed on the surface. And these loops of current, which are formed on the surface of a conductor due to changing magnetic flux, is what we call eddy currents. And I thought that these are called eddy currents because maybe some guy named Eddie discovered it, because that's how most of the stuff works in physics. But they're called eddies because they are swirling. So if you consider a whirlpool of water, something that's swirling, they're usually called eddies or vortices. And since this is very similar to that, we call them eddy currents. But how does that produce any heat? Well, of course, current produces heat. We've learned that before. When current flows through a wire, the wire heats up. Now there is current everywhere on the surface of the conductor, which means this whole metallic plate heats up. So if we go back to our vessel of water, due to the fluctuating magnetic fields, eddy currents are set up on the base of this vessel. And that's how the vessel gets heated up directly. And then that heat is transferred to the water, making it boil. Well, then why doesn't that same thing happen to our hands? Well, that's because our hands are not all that great conductor. And therefore, the eddy currents formed are incredibly microscopic and they hardly have any effect. So in short, these induction cookers generate fluctuating magnetic fields. And when there is a conductor nearby, it experiences a changing magnetic flux that induces currents on the surface, which we call the eddy currents, which heat it up. And that's how you can have induction heating. Incredible, isn't it? But wait, before we start parting, doesn't it mean that whenever you have conductors and changing magnetic fields, you will have eddy currents and as a result you will have heating, even if you don't want them? Yeah. Wouldn't that be a problem? What if you don't want that to happen? How do you reduce eddy currents when you don't want them? Again, going back to our metallic plate, how do we reduce these eddy currents when we don't need them? Well, we can reduce current by increasing the resistance of our metallic conductor. We know more resistance means less current. How do I increase the resistance of this conductor? Well, one of the cool ways of doing that is by introducing slots like this. So kind of making it like a comb. In doing so, think of what we are doing. We are introducing air in between, and air is an excellent insulator, which means the overall resistance of this now has increased tremendously. And as a result of that, the eddy currents now have reduced tremendously, which means less heat loss. And this also means now there is less area for the current. So you'll have tinier eddy currents. And again, because of this, we'll have less heating effect. And a practical application of this is seen in transformers. Now, the details about the working of transformers is something that we'll tackle in a separate video. But the important thing is transformers also have changing magnetic fluxes, and they have this you can see this giant conductor in between, which means there will be eddy currents formed over here, and we don't want the heating effect to happen over here. So how do we reduce it? Well, the whole idea over here is instead of having one giant block of metal where eddy currents can keep dancing wherever they want, we instead have thin slices of these metals laminated and then glued together. In doing so, we are introducing air, just like over here, and as a result increasing the resistance, thereby reducing the eddy currents. And because these things are all laminated, there is no electrical contact over here, which means you can't have a lot of eddy currents over here. So in doing so, we dramatically decrease eddy currents, and as a result, we dramatically decrease heating losses. So now, we not only know how to use eddy currents to heat up things, but we also know how to reduce them when we don't want them. But wait, there's more. Check out this demo. In this case, again, we have an electromagnet which is going to generate fluctuating magnetic field due to the alternating current, and he's pressed that, so it's switched on, and then he's going to put an aluminum ring on top of this and see what happens. Here we go. And voila! Notice the ring just stays there. It's levitating in air. Beautiful, isn't it? Why is it doing that? And see what happens when it lets go of it. It falls down. So why is it doing that? Can you pause the video and think a little bit about this as to why the ring was levitating? Alright, let's go back to our drawing board. Here is that picture of levitation one more time. Why is the ring staying in the air like that? Well, again, this electromagnet is generating a magnetic field. There's a current running and it generates a magnetic field, but importantly, it's generating a fluctuating magnetic field, just like with the induction cooker. And as a result of that, we have a conductor placed on top of that, and just like how we saw, there's going to be eddy currents. So there'll be currents running on the surface of that aluminum coil. But what does that cause levitation? Well, remember, this current loop itself starts behaving like a tiny magnet. So this aluminum ring now behaves like a magnet. And now from Lenz's law, we've seen that the current induced will be in such a way that it tends to oppose the cause for it. So when you apply Lenz's law, it just turns out that the magnetic field that it generates opposes this. And as a result of that, this starts repelling this magnet. And for that reason, once that repulsion is stronger than gravity, it starts staying in the air. Magnetic levitation. And one of
Air pollution consists of chemicals or particles in the atmosphere that pose serious health and environmental threats. But what causes air pollution, and what does it mean for our planet? Some air pollution comes from natural sources like volcanic eruptions, wildfires, or allergens. But most air pollution results from human activities, such as energy use and agriculture. There are different types of human-made air pollution. When we burn fossil fuels to produce energy, they release greenhouse gases into the air. These emissions, such as carbon dioxide, methane, nitrous oxide, and fluorinated gases, trap heat from the sun in Earth's atmosphere, leading to a rise in global temperatures. This creates a cycle where air pollution contributes to climate change, and climate change creates higher temperatures. In turn, higher temperatures intensify some types of air pollution. For example, climate change increases smog because it forms in the presence of high heat and increased levels of ultraviolet radiation. More frequent extreme weather, such as flooding, contributes to damp conditions and therefore to a rise in mold. Warmer weather also leads to longer pollen seasons and therefore more pollen production. Smog is a type of air pollution that reduces visibility and has serious health effects. Smog can be divided into two categories: sulfurous and photochemical. Sulfurous smog is made up of chemical compounds called sulfur oxides. It occurs when burning sulfur-bearing fossil fuels such as coal. Photochemical smog, also called ground-level ozone, is a result of the reaction between sunlight, nitrogen oxides, and volatile organic compounds. Nitrogen oxides come from car exhaust, coal power plants, and factory emissions. Volatile organic compounds are released from gasoline, paints, and many cleaning solvents. Smog not only creates a brown haze that reduces visibility, but also harms plants, irritates the eyes, and causes respiratory distress. Another category of air pollution is toxic pollutants. These are chemicals such as mercury, lead, dioxins, and benzene that are released during gas or coal combustion, waste incineration, or burning of gasoline. In addition to adverse environmental effects, toxic air pollution can cause serious health problems such as cancer, reproductive complications, and birth defects. While air pollution has many consequences for our planet, there are solutions. We can limit toxic pollutants, smog, and greenhouse gases by decreasing the use of fossil fuels, such as in transportation, manufacturing, and electricity generation. Reducing air pollution not only contributes to a cleaner environment and better human health, but can also slow the rate of global warming.
The impact of air pollution on children's brain development and health. The small smoke particles from air pollution, or PM 2.5, are more than 25 times smaller than the width of a human hair. As air is inhaled, particles enter the body through the nose and mouth. Air passes through the respiratory airway and finally reaches the alveoli, tiny air sacs in the deepest part of the lung. The smallest of the particles that enter the lungs diffuse through the walls of the alveoli into the bloodstream, but they are transported to all organs of the body where they can affect normal function. Critical organs affected include the lungs, immune system, heart, and developing brain. The growth rate of the brain is highest around birth, but development continues throughout childhood and adolescence, playing an important role in a child's memory, attention span, emotional control, and social interaction. Once in a child's still developing brain, particulate matter damages brain cells. The result: impaired cognitive development and ability to learn that may have severe consequences for welfare and earning potential across the lifespan, and may accumulate, resulting in neurodegenerative disease later in life. In addition to harming the brain, exposure of the fetus to air pollution may increase the risk of other diseases across the lifespan, including stroke, pneumonia, ischemic heart disease, chronic obstructive pulmonary disease, lung cancer. Protect your children from air pollution. Stay inside when air pollution is high. If you have to go out, wear a filtering mask. Install window filters and air filters at home if possible. Consume food and drinks high in vitamin C, E, and omega-3 antioxidants.
Honeywell HPM series particle sensors use laser-based light scattering detection to quantify particulate size and concentration in real time. The HPM series enables more cost-effective and accurate measurement and control of particulate contaminants in air conditioners, air quality monitors, environmental monitoring, and air cleaners, and features a particulate concentration range of 0 to 1,000 micrograms per meter cubed. The sensors output data based on PM 2.5 detection, but can be reconfigured for PM 10 detection. Honeywell HPM series particle sensors offer an industry-leading 20,000-hour rated operating time, and their enhanced reliability allows for use in harsh environments.
Today I'd like to talk about this sensor from Honeywell. It's a PM 2.5 sensor. It measures 2.5 micrometer particle in the air, and it can also give you PM 10 reading, so you can get to different PM reading from this sensor. When you order from Cytron, you'll get this sensor module, you get the cable and a board that we have designed with a proper level shifter connector for the sensor and also groove, and a power input using a micro B USB connector. It's quite common for Android phone and also power bank charger. So there's a switch over here. You need a UART to grab the data, the serial. I'll put a link for the data sheet and also product and also example code for Arduino under this video. So do check it out. Let me show you how to use it. Get started easily. So you can actually get a separate OLED from our store. It's as you can see, just solder 4 pin over here to this breakout board and power this board using a micro B from your, let's say, your power bank or your phone charger. So you'll actually power up the sensor right away. You might need to wait for around 10 to 15 seconds before the reading is stable. So anyway, if you are good with the display and you don't want to use it, you can actually turn this switch, the slide switch over here, turn it to groove mode, then you bypass this OLED and the signal will go through your groove connector. Okay, so I hope this video helped you, and
The Zensiv Pass CO2 sensor is able to detect the level of carbon dioxide in indoor spaces. How does it work? Pulses of light from an infrared source pass through an optical filter tuned specifically to the CO2 absorption wavelength. The CO2 molecules inside the measurement chamber absorb the filtered light, causing the molecules to shake and generate a pressure wave with each pulse. This is called the photoacoustic effect. An Infineon Zensiv MEMS microphone with an exceptionally high signal-to-noise ratio is placed inside the absorption chamber and detects these very small changes in pressure. An integrated microcontroller converts the MEMS microphone output into a CO2 concentration reading.